Welcome to The Explainer. Today, we're going on a seriously fascinating journey. We are going to look at how we translate our chaotic, infinitely complex physical world into perfectly structured digital code. Basically, we're exploring the invisible architecture that literally runs everything around us, from global shipping logistics right down to your morning commute.
Think about it for a second. How exactly does your smartphone know instantly how to route you around a sudden traffic jam? And not just that, it's navigating you across the surface of a curved planet, all while processing data that's being beamed down from space. It is a massive computational feat. The magic behind this everyday miracle is Geographic Information Systems, or GIS. It's this incredible technological framework merging geography with computer science. And today, we're going to break down exactly how it all works.
Okay, let's dive into this. Here's our roadmap for the explainer. First, beyond traditional maps. Then, flattening a 3D Earth. Number 3, the power of layers. 4, raster versus vector models. And finally, fueling GIS with data. We're zooming in step by step from the literal shape of the Earth all the way down to pixels and vectors.
Starting with Section 1, Beyond Traditional Maps, the Evolution of Spatial Data. And right off the bat, we need to understand that GIS is a massive step beyond just drawing traditional static maps.
It's really an engine of integration. It reads, edits, stores, and dynamically analyzes spatial data. Now, spatial analysis has actually been around a lot longer than computers. Let's blitz through the history real quick. Back in 1854, physician John Snow created one of the first examples of analytical cartography. He mapped a cholera outbreak in London to pinpoint its waterborne source. Pretty groundbreaking, right? Fast forward to the 1960s, and Roger Tomlinson, who is widely known as the father of GIS, invented the Canadian Geographical Information System. That brought spatial data into the mainframe era. And today, we have evolved into this massive era of global web mapping, where massive databases and GPS networks are literally accessible to anyone holding a mobile device.
Moving to Section 2, Flattening a 3D Earth, Geodesy and Projections. This brings us to our first macro challenge. How do we define the shape of a massive, bumpy planet?
Because Earth is definitely not a perfect sphere, applying a standard mathematical grid to it is a monumental scientific hurdle. And this brilliantly illustrates what we call geodesy. Notice the visual contrast between these three fundamental surfaces. First, you've got the physical Earth's surface, the actual mountains and valleys you stand on. Then below that, the blue line represents the geoid. This is a highly complex surface based purely on equal gravitational attraction. It's essentially where the ocean level would sit. Finally, that dashed green line is the ellipsoid. This is a smooth, mathematical model of the Earth's shape that our computers can actually calculate to establish coordinates.
To make all this complicated math align with reality, we use a Coordinate Reference System, or CRS. A really crucial component of this is the datum. You can kind of think of a datum as a physical anchor. It links our smooth mathematical ellipsoid to that bumpy gravitational geoid at a specific fundamental point. That anchor is what gives us a highly accurate coordinate reference system, which lets us pinpoint any location on Earth with remarkable precision, like the WGS-84 system that your car's GPS relies on.
But here's the catch, and it's a big one. The Earth isn't developable. In geometry terms, that means a sphere or an ellipsoid just can't be flattened out without stretching it or tearing it. So when we project these 3D coordinates onto your flat 2D phone screen, something has to give. Projecting these coordinates will always warp area, shape, or distance. Take the popular Mercator projection, for example. It drastically distorts the size of Greenland, making it look basically as large as Africa. In reality, no way. Africa is about 14 times larger. So, depending on what a cartographer needs their map to do, they have to carefully choose an equal area, conformal, or equidistant projection, constantly balancing those inevitable distortions.
All right, Section 3, the power of layers, organizing reality. So, how exactly do we organize all this flattened data without it becoming a total mess?
Now, what's really interesting about this slide is the layer cake metaphor. In a traditional printed map, everything, the roads, rivers, city names, elevation, is just smashed together on one piece of paper. But GIS completely divorces the data from its visual representation. It stacks thematic variables into independent, transparent blocks. You can isolate just the elevation or the land use, soil type, or hydrography, and then combine them seamlessly without any of the clutter. Honestly, this atomic organization is the true backbone of all GIS analysis.
And this organization builds directly into something called cartographic generalization.
Think about it. If a program rendered every single side street and alleyway while you were zoomed way out looking at a map of the entire globe, your screen would just be a solid, illegible block of tiny lines. Instead, GIS smartly uses multi-scale layers. As you zoom out, the system automatically aggregates, simplifies, or just completely drops less important features. It adapts the data dynamically so your map remains useful, fast, and legible, no matter what scale you are working at.
Section 4. Raster versus vector models, drawing the digital world. So we have our flat map and our smart layers, but how does the computer actually draw the roads?
Welcome to the great data showdown in GIS. We're talking raster versus vector. The raster model relies on continuous grids of pixels to cover a space. That makes it absolutely perfect for sprawling, continuous variables like elevation or temperature. Vector, on the other hand, uses discrete geometries. We're talking precise points, lines, and polygons. This makes vector data ideal for tracking distinct real-world features, things like property lines, roads, and buildings. Let's look a little closer at raster. Notice the sort of stair-step look of these grid cells. In a raster model, the whole space is systematically divided up into a grid, and every single cell holds a specific value. Now, while it looks pretty chunky and honestly terrible for drawing precise curves or sharp property corners, its real strength lies in mathematical matrix analysis. Because it's just a uniform grid of numbers, it is perfectly suited for computing things like the slope of a mountain or analyzing satellite image color bands. Now contrast that immediately with the vector data model. Here, the space isn't divided up at all. Instead, the computer plots discrete coordinates and uses distinct lines to trace the absolute precise boundaries of features in the real world. If you are tracking a winding river or a really complex city block, vector polygons and lines give you the exact shape. And what's super cool is that each of those shapes can hold an entire database of attributes. So a road's name, its speed limit, its lane count can all be attached to one single geometric line.
So the crucial point is that just drawing a line isn't enough for advanced GIS. Look at the spaghetti data on the left. The lines cross, sure, but the computer has no idea if they intersect at a four-way stop or if maybe one is an overpass bridge. But by adding something called topology, which you see on the right, we define the spatial relationships and connections between those lines. Topology is exactly what allows your GPS app to understand turn restrictions and intelligently route you through a totally chaotic highway network.
Okay, final section, number 5. Fueling GIS with data, capturing the planet. We've talked about how the computer models, flattens, and draws all this stuff, but where do we actually source all this digital raster and vector data from in the real world? Well, a vast majority of modern GIS data comes from remote sensing. That is, acquiring information about the Earth without ever physically touching it. And this is done in two main ways. First, you have passive sensors, like the cameras on satellites. They simply capture the natural sunlight reflecting off the Earth. Active sensors, on the other hand, are a bit more aggressive. Technologies like LiDAR actively emit their own light pulses or radar waves down to the surface, and they measure exactly how long it takes for that energy to bounce back. But capturing this data involves constant trade-offs for aerospace engineers. It's all driven by 4 types of resolution. Spatial is how small of an object you can actually see. Spectral is the number of light bands captured, like infrared or ultraviolet. Radiometric is the sensitivity to slight color differences, and temporal is how often the satellite orbits back over that exact same spot. Because of technical limitations, you can literally never maximize all 4 at once. For example, if you want extreme spatial detail to spot a single car on a road, you have to sacrifice temporal resolution, meaning your satellite might only capture that specific spot once a month. So GIS experts are constantly blending data from different sensors to get the complete picture.
From early scientists mapping cholera on paper, to understanding the gravity-warped shape of our Earth, right up to lasers bouncing off the planet from space, GIS is truly how we make sense of our world. We've essentially wrapped the physical globe in this invisible, digital layer of intelligence. As we integrate ever more real-time mobile technology and microsatellites, the question isn't just about how we map the world today. It's really about this: what invisible layer of our reality will we map next? Thanks so much for joining me on The Explainer, and as always, keep questioning the world around you.